All right, today we're going to be talking about what's called linear programming or also optimization. These are more of a real world kind of example of how we can use systems of equations and what they could be used for doing. Obviously, the problems that we're going to be working with here today are significantly smaller than what a real world problem would be, but the idea is still the same. So, what are we going to be doing today? We're going to be finding the maximum and minimum values uh, for a function over a given region. And then we're going to do real world optimization problems using what's called linear programming. Now, I did go ahead and give you a few um, videos to go ahead and watch in terms of the appropriate keys to hit on the uh, graphing calculator, but I have some examples obviously here. So, what are the steps that we're going to go ahead and do? First, we need to define any variables that we need to. Now, some of the problems will just have them, but like our word problems, we'll need to go ahead and do step one. And step two, write the systems of equations of inequalities. The thing with what we're going to be doing today is we're going to have multiple inequalities. So it's more than just going to be the two that we've done before. We're going to do 2, 4, 3, 4, 5, whatever it is, and we're going to get different kinds of shapes, quadrilaterals, triangles, pentagons, and things of that nature. So we're going to need to graph our system of inequalities. Now be careful when you're graphing them, because when you graph them, remember your calculator's window is a 10 by 10 window. It goes to positive 10 and negative 10 and so on and so forth. So if you have numbers, especially with real world examples, that are significantly higher than 10, you might have to zoom out or go to your window set and set it specifically for certain values so that you can find the graph as a whole. We're going to find the coordinates of the vertexes of the feasible region. We're going to have a linear function that needs to be maximized or minimized. We're going to substitute those values into that function. And then we're going to select our result, the greatest or least, to whatever answers the problem. Now, some of them might be we want the highest, or sometimes we want the lowest. The practice problems that we're going to do, we're going to ask for both of them just so that you can do that. But what do I mean by that? Like, if we're solving this problem to optimize the amount of profit, we want the biggest amount of profit. If we want to optimize the amount of cost that we're going to spend, we want the least amount so that we can maximize what we want to do. So that's what these problems are all about. So let's start with some basic ones. Well, we need to talk about two different possibilities that we can have, and we're going to talk about the feasible regions. Most of the time, we're going to be bounded. We're going to have constraints. If we have 3 constraints, we'll form a triangle. If there's 4 constraints, we'll do a quadrilateral, and so on and so forth. Each of the corners are called vertices. A single one is called a vertex, but multiple ones are called vertices. And these vertices are the most important parts of the feasible region, because those are where the maximums and minimums occur. All the values on the inside are possibilities, but all of them will not give you a maximum or minimum. Now, notice there are 3 points here. One's going to be the max, one's going to be the min, and one's just going to be another value somewhere in the middle. This could be the max, this could be the min, or this could be the max, depending upon the type of formula that we go ahead and we plug into. So just because it's down here and it looks like it might be the minimum, it doesn't necessarily have to be. Again, we have to plug in the points and find out which one it is. So we are going to have more than enough points, but like I said, one is going to be the max and one's going to be the min. Now, it is possible that we have an unbounded region, and you should notice that these are parallel lines over here. If we do have parallel lines, it is possible for us not to get a closure on this other side. And so these lines would not close and not form that extra point down here. And because of that, this goes on and on and on. Unbounded regions will have a maximum or a minimum, and then the other one won't exist because it's unbounded and it goes on forever. We'll have an example of this type to show you what I mean. Let's start with these bounded regions. So here's a system that we have, and here's the profit or cost equation that they have in here, the function that we are going to go ahead and find the maximum or minimum for. And they're saying it's 3x minus 2y. Maybe you get $3 for every x, and it takes 2y's to go ahead and make those, or some combination. It's unimportant what the exact values are. But this is the formula that they have that we're going to take our corners, our vertices, and plug into. So this formula here, notice how it has an x and a y, and f of x and y, because we're plugging in x and y to it. This one we don't deal with, we don't graph it at all. So we're just graphing these three here. So we're going to graph x is less than 5, and of course we go up to the top left of our calculator and get that, and the y equals 4, and this one here we're going to have to solve for y. So we have those three equations, so we have three equations, so we should get some sort of like a triangle. And that's exactly what we end up getting here. Your graph should look something like this. Now you do need to, so that's the step, the first major step is to graph those inequalities. So once we have the inequalities graphed, we're going to need to find the vertices. So you have to use the intersection part of your calculator, second calc intersection, tell it which lines you want to have intersect, and it will go ahead and give you those different points here. So we have -2, 4, 5, 4, and 5, -3. So those are the 3 points that we have. Now those 3 points are going to get plugged into this formula, this equation here, this function, and that's what we're going to try to find the max or mins for. So we're going to kind of create a table here in just a moment. But the whole part of this graph is to find those 3 points. All right, so here's our table with the 3 points that we have, the 3 vertices. And here's the formula. That should be a 2y here. They put the 2 in there, but they forgot to put the 2 here. So -2 in for x and 4 in for y, and that gives us a -14. Plug that in, we get a 21 and a 7. Even though 5, 4 kind of looks like it would be the best, it actually isn't. So our maximum is here at 5, -3, giving us 21. And our minimum here is -2, 4, which is -14. Probably don't want to have that kind of a profit, -14 bucks. 21 sounds a lot better. So minimum and maximum. And so we can go ahead and say the maximum is 21 at this point, and the minimum is -14 at this point. And let's try another one. Here we have 3 different equations again. X is less than 4, y is less than or equal to 5, and x plus y is greater than or equal to 6. So again, we just kind of graph the boundary lines. So I've graphed them here, and we're talking about this interior section here. Using the equals just makes it a little bit easier to see, because a lot of times you'll have all this crossover with the graph. So if it becomes difficult to see, just use equals like I have here. So I have those equals, and now I just need to find those corners. So this one here is 1, 5. So there's the 1, 5, and we have 4, 2 for that intersection there, and 4, 5. So those 3, then I make my little table and find out which one's my max. My maximum here is 10, and my minimum is -11. Now what happens if we do have that unbounded region? So again, here's our formula that we're going to plug into. Again, that does not get graphed. So we just have these 3, so it should be a triangle. But each of these are going to need to be solved. So we have to go ahead and solve them each for y equals, so we can put them in our graph. But once you've done that, you notice that this is our region here, and these two end up being parallel. Well, being parallel, they never intersect. They don't form that third part of the triangle. So I've got these 2 points, 0, -2, and -2, 0. Well, those are the ones I'm going to put in here. And one of them is going to be a maximum or a minimum, and then we won't have the other one, because somewhere up here will be, these values will either keep going higher and higher and higher, or they'll keep getting lower and lower and lower. We have to, of course, go ahead and find out which one is which, but we'll do that in just a moment. So we're going to go ahead and make a table again. -2, 0, and that gives us -4, and 0, 6 gives us -6. Now, the -6 is a minimum. Well, how do we know that it's a minimum and not -4 being the maximum? What we need to go ahead and do is to what follows here. We're going to go ahead and try some other points like 2, 1 or 3, 1. If we look back at our problem here, 2, 1 would be right here, and 3, 1 would be right here. So these are points that are inside. We're kind of pretending that this is our third spot. We know that there isn't one, so any of these points in here, so 2, 1, 3, 1, 4, 2, any of those points we could use. Doesn't matter. But I need to test one. So we have 4, 2, 1 gives us 7, 3, 1 gives us 10. So what's happening to our values? They keep getting bigger and bigger and bigger. So there is no max value. So then I have to look at these and find out which one's the minimum. And that's the 0, -2. So that's how I decided that this was a minimum value at -6, and that not being a maximum value at -4. Because we didn't know whether it was keep getting bigger or smaller, so we have to test points. So there is no maximum. The minimum is -6 at 0, -2. All right, so let's try one with an actual problem. Now again, these are relatively simple problems, but I'm going to walk through them with you. There are 2 different ones. So first we're going to do a landscaping company. It has crews that mow lawns and prune shrubberies. The company can schedule 1 hour for mowing jobs and 3 hours for pruning jobs. Each crew is scheduled for no more than 2 pruning jobs per day, and each crew is scheduled to set up for a maximum of 9 hours per day. On average, the charge of mowing the lawn is $40, and the charge for pruning is $120. Find the combination that makes them the most money, because that's what we want to go ahead and do, right? We always want to make the most money. So let's go ahead and talk about defining some variables. Well, we have mowing jobs and pruning jobs. So mowing for M and P for pruning. Now in terms of X and Y, we're just going to do alphabetical. So M is like X and P is like Y, if that helps or makes it easier for you. So we're going to write some systems. So what are some things that we can't have? Well, jobs can't be negatives. We can't have less than negative. We can't have -1 mowing jobs. So because of that, we know that they have to be greater than or equal to 0. When we go ahead and we do these problems that are actual optimization problems and real world problems, we're always going to have these constraints. It's always got to be greater than 0 because we can't have negative of things in real life. All right, mowing jobs take 1 hour, pruning jobs take 3 hours, and there's 9 hours to do the jobs. So 1 times the amount of mowing and 3 times pruning. So 1 mowing, 3 pruning has to be less than or equal to 9. And we can't have more than 2 pruning jobs, so we have to have pruning is less than 2. So we've got a couple of equations here. We actually have 4 of them. So if there's 4 of them, we're going to get some sort of quadrilateral. So let's go ahead and graph these. So if we graph it, notice we do get a quadrilateral. And so we have y equals 2, y equals 0, x equals 2, and then this line here. And we have 4 corners. Now we probably are pretty positive that if we mow no lawns and do no pruning, we're not going to make the most amount of money. But it is a possibility in here. Obviously, it's our minimum possibility, and that's not one we want. We want a maximum. But that is a possibility of something that we can do. We could do nothing. All right, so let's take those 4 points and go ahead, and how much are we getting paid? We're getting $40 per mowing and $120 per pruning. So this is our formula, and now we're just going to try each of them in there. So here's our table, 0, 2, 3, 2, 9, 0, 0, 0. Well, 0, 0, of course, gives us no profit. We didn't do anything. 0, 2 is 240, but we have 2 360s here. So in this case, either of those options are the best. Either do 9 mowing lawns or 3, 2. So either of those, whichever one you want to do, would receive the most money. So that's how, if you're going to schedule things for your company, that would maximize your profit. All right, what about this one? A company makes widgets and plinkets. I don't know what a widget is or a plinket is, but they do make them. So a company profits $3 for every widget and $2 for every Plinkett. It must make at least one widget and one Plinkett per hour and cannot make more than 7 total in an hour. What's the most profit that a company can make? All right, so widgets and Plinkets. So W and P, again, I'm going to do that alphabetical. So W and P, W is the Y and P is the X. So W here has to be greater than 1. That's one of the things that it says. You must have at least one widget. So we don't need the 0 there because it's already saying we're making 1, and we're also making 1 Plinkett. But it also says we can't make more than 7. So Plinkets plus widgets has to be less than or equal to 7. Again, I go ahead and make them equals, move this one over, so it's Y equals, and so 7 minus X. So here's what I get a triangle because I had 3. So I had these two in here. So where are my ordered pairs? I can make 1 and 1, 1 and 6, or 6 and 1. Going ahead and doing that, the most profit is here with a 20. So $20 by building 1 Plinkett and 6 widgets. And that's what I have for you today.